Okay, we're talking about continuity today, whether or not a function is continuous. Well, a particular function is continuous if it satisfies three conditions, and the conditions you can see there on the screen. The first condition is that the function has to be defined at that particular point. In other words, there can't be any domain issues or anything like that. Most common domain issues are, you remember that you cannot divide by 0, and also remember that it's impossible to take the square root of a negative number. There can be other problems, but those are some of the most common. So the function obviously has to be defined and to make sense in order for the function to actually be continuous. The second condition is that the limit as x is getting really close to that point A of the function has to exist. And then the very last condition that you have to meet in order to satisfy continuity is that that particular limit, not only does it have to exist, it also has to be exactly the same thing as what the function would be equal to at that point. Now, when checking for continuity, you actually have to check all three conditions. And if all three conditions are checked off, then you can say a function is continuous at that particular point. If any one of those three are not satisfied, then it fails and the function is not continuous. Just as an example of a particular function, let's suppose that function looks like this. Maybe it's a piecewise defined function. So it goes along like this, stops at x equals 2, y equals 2, and has a closed circle there. And then the function actually changes, has an open circle here, and then goes on from there. Well, first off, notice that this is still a function because it passes the vertical line test, but it doesn't look like a continuous function. But what you can do is you can check the conditions on the left to see. Well, if you consider condition 1, you need to have the function defined. Let's suppose we're concerned about that point, a equals 2. That's where we're most concerned about whether or not this is a continuous function. Well, the first question says, is it defined? Well, f at 2 is defined, and if you look at the graph, it's equal to a y value of 2. So the first condition is satisfied. There is actually a defined function value at a equals 2. The next question is looking at the limit. Well, the limit as x values get close to 2 of the function, this one, if you look at this limit, does not actually exist, because if you come from the left, it goes towards a y value of 2, and if you come from the right, it goes towards a y value of 3. So since 2 is not equal to 3, the limit does not exist. So therefore, the function fails condition 2, and so therefore it's not a continuous function. Notice that we don't even need to check condition 3 because the limit doesn't exist, so we can't even see if it's equal to f of a or not. So at this point, we can just stop and say that this particular function is not continuous. a equals 2. Now, let's consider a different example. Let's suppose that instead of changing into a different function, let's suppose that the function is just happens to not be defined at x equals 2 to begin with, and then we fill it in up top at y equals 3. So again, this is technically a function because it satisfies the vertical line test. But if you're going to check for continuity, you got to check the 3 conditions. Well, condition 1 is that you've got to check that f of a is defined. And again, suppose that we're interested in the value 2, because that's where it looks like there's potentially a problem. So if we're checking for continuity at 2, well, to begin with, we need to figure out if the function is actually defined at 2, because if it's not defined, there's no way it's continuous. Well, if you look, when x is 2, the function is taking on a y value of 3. So f of 2 is 3, it's defined, there's no issues there. So there's no domain issues, the function is defined at 2. Condition number 2, we want to see if the limit as x approaches 2 of the function makes sense. Well, remember that the limit exists if the limit from the right equals the limit from the left. Well, as x is getting really close to 2 from the right, we're going towards a y value of 2. And as x approaches 2 from the left, notice how we're still approaching a y value of 2. So the limit does exist and in fact equals 2. So there's nothing wrong with condition 2. That has been satisfied. But remember, for continuity, you have to have all 3 conditions satisfied. Condition 3 would be that the limit is actually equal to the value of the function. Now remember, in this case, the limit was equal to 2, and the function itself was equal to 3. So is 2 equal to 3? Definitely not. So the third condition failed, so this is not a continuous function. So on this one, we actually got all the way to checking the third condition, but it failed on the last one. Now, as just a general description of whether or not a function is continuous, a function is continuous if you can draw the function without actually picking up your pencil. Now, that's not the mathematical definition of continuity, so you can't use that to verify continuity. But if you want to just take a quick glance and decide if a function is continuous or not, you can look at the graph, and if there's no point where you have to pick up your pencil to draw it, then it's going to turn out to be a continuous function once you check the 3 conditions. So, for example, if you looked at the function y equals, say, x squared, we all know that's just a parabola centered with vertex at the origin. So y equals x squared looks about like this. And it is a continuous function. And you can check all 3 conditions at any one of the points, and it will pass. So remember, when you're watching this video, you will need to pause in order to take notes. So be sure that whenever I move too fast for you, just pause, rewind, rewatch, and take notes. You should have a piece of paper and pencil out and your calculator as you're following along through this lesson. But if you're ready, we can go ahead and go to the next topic. The next thing we're going to discuss is a particular theorem that tells you whether or not combinations of functions are also continuous. The idea with this theorem is it's most useful if you already know a particular function is continuous, then you can figure out if combinations of that function with another function preserve continuity. What this potentially does is it potentially saves you from checking those three conditions over and over again for complex functions. Consider, for example, y equals x squared. Well, we know that's a parabola. Centered at the origin, it is continuous. Similarly, another function, and let's start over there. Didn't mean to delete the whole thing, but that's okay, it's not that big of a deal. Let's call one of these functions f, so that we're using a consistent notation here. So f equals x squared, as I said before I erased it, that was a parabola centered at 0. Let's consider another function, g of x. Well, let's suppose that g of x is the function x plus 4. Now we all know that that's just a straight line with slope 1 and y-intercept 4. So that's actually not a perfectly straight line, but I think if you can use your imagination, that's what it looks like. Then any combination of f and g listed below is still continuous. Again, we know that what the graph of x squared looks like. It's a continuous function. We know that g of x equals x plus 4 is a continuous function. Well, then any one of these combinations here on the left is also continuous. So for example, f plus g at x. Well, if you take the function f and add on the function g, that new function is really x squared plus x plus 4. So we know that x squared plus x plus 4 is also continuous without actually having to check it in any sort of way. So as you can see, any combinations of addition, subtraction, multiplication, division, stuff like that's still continuous. But since I've mentioned division, let's look at this one real quick. So f over g. Well, in this particular example that I made up over here, f over g is going to be the f function divided by the g function. Now notice how they mention that f over g is only continuous where the denominator is non-zero. Why is that? Well, remember that one of the conditions of continuity is that the function has to be defined at any particular point that you're interested in. Well, whenever you have a denominator, remember you're not allowed to have denominators equal to 0. So this particular function that I just put right here, f over g, has a problem. It is not defined at x equals -4 because that would make the denominator 0. So f over g is continuous except at -4. So if you're going to divide functions, you need to be careful about that and make sure you consider that the denominator cannot be 0. The next condition on the list is that you can multiply by a constant and still have continuity, so that saves you work. If all you're doing is multiplying by a constant, there's no problem. You can also preserve powers of the function. Here we're assuming n is a natural number, so n is just 1, 2, 3, 4. So you don't have to worry about taking a power of a function. The only exception is if you're taking a fractional power, like for example square root, you do need to worry about that because you cannot take the square root of a negative number. So if you're looking at, say, a fractional power like square root of f of x, you need to be careful. You might not automatically have continuity. But be sure that, again, pause the video if you need to and make sure that you write down this theorem. And you're free to use it whenever it's useful to you. But if you are ready, we're going to go ahead and keep going. So make that go away. Go to the next slide. So we got a particular example here where we're given a function and we're asked to determine if it's continuous at a particular value, in this case a equals 3. Now they want us to not just graph it and look at the picture, they want us to actually go through the 3 mathematical conditions for continuity. So again, don't just graph this in your calculator and look to see if it looks like a smooth curve. They want you to actually check the 3 conditions according to the instructions. So let's do that. Since this is a rational function, rational meaning ratio, we have a denominator, which means that you need to consider if the denominator is going to be 0 or not. That's a big deal with rational functions. Well, in this case, sorry, it's not an x squared, that's an x. Well, in this case, we've got a denominator that could potentially be 0 depending on the x values. Whenever you see a quadratic expression, that's an x squared expression, you should probably try and factor it. They're not all factorable, but it's usually a pretty good technique to try that. So let's factor the denominator, and we should be able to get the zeros of the denominator, and that would alert us to any potential problems in the function being defined. Well, two numbers that multiply to give you positive 12 and combine to give you negative 7 are, of course, negative 3 and negative 4. Notice how there's no cancellation, so we didn't get anything like that. But we do know where the denominator is 0 now. So notice that this particular expression is not defined at 3 or 4. Any other x values would be fine, though. However, look where we were asked to see if it was continuous, right at 3. So there is a potential problem here. The function is not defined at 3. So when you went to go check the 3 conditions for continuity, remember condition 1 was that f of a is defined. Well, in this situation, f of a is not defined, so therefore the function is not continuous at a equals 3. So we didn't have to bother with condition 2 and 3 because we've already failed it at condition 1. Remember, we're only continuous if you satisfy all 3. So once you find a failure, you can stop there. There's no reason to check the other conditions. So if you guys are ready, we'll go ahead and go to the next problem. So looking at example 2 here, notice that f of x is defined as a piecewise function. Well, whenever you've got a piecewise function, it's probably a good idea to try to graph it, at least a rough sketch. That's the easiest way to see what's going on. After that, we'll go ahead and start looking at the 3 different conditions. However, if you'll pay attention to the first part of the function, the part where x can't be 1, notice that that numerator can factor. Into x minus 1, x plus 1. And what you're going to get is a cancellation of the x minus 1s. So that first function is equivalent to the function x plus 1. The only difference is that we're not allowing it to equal 1. So graphing this piecewise function, what it looks like is it looks just like the function x plus 1. Well, that's a line, right? There's no x squared or x cubed there. It's a line of slope 1 and y-intercept 1. So it definitely goes through the y-axis at 1, and then rise over run, so you rise 1, run 1, there's the next point. This is the function y equals x plus 1, right? But remember, they're not allowing it to equal 1 exactly, and this is only according to the specifications in the definition of the piecewise function. So this particular function actually has a hole in the graph when x equals 1. So the original function x squared minus 1 over x minus 1 has a hole in the graph at x equals 1. And that makes sense because it would make the denominator 0 in the original expression, so we can't allow it. But when x is 1, they do give us an instruction to make the function value 3. So what happens is this particular piecewise function looks like that thing on the left. So you've got a straight line with a hole, and the hole is actually filled in up above. Now notice how you cannot draw that graph without picking up your pencil. If you tried, you'd actually have to pick up your pencil to put the 3 in and then go back down. So we suspect that this function is not continuous because of that. But we're going to still check the conditions according to the instructions in the problem. Now remember, the first condition is that we have to be defined at that a value. Well, in this particular situation, they're asking us to look at f of 1, right? Now, f of 1 is defined. Why? Because f of 1 is equal to the number 3, right? It's right up here. F of 1 is on there. There's no problem with it. Condition number 2 is that we need the limit at that particular potential problem of 1 to exist. Well, the limit of the function as x gets really, really close. Remember, we're getting close to x equals 1 here. The limit from the right is 2, right? Because the y values are getting close to 2. And the limit from the left is also 2. So the limit as x gets really, really close to 1 of that function is 2. Remember, it doesn't matter what the function is defined to be at 1, just what happens when you're getting really close to 1. Well, when you're getting really close to 1, the function is approaching 2. So far, so good. But if you go and check that third condition, what happens? Remember, the third condition is that the limit has to be equal to the function value. But in this case, that's not true because 2 is not equal to 3. So even though we satisfied condition 1 and condition 2, we did not satisfy condition 3. So the function is not continuous. Oops. So that's it. It's continuous everywhere except for that x value of 1. That's where the problem is occurring. All right, so let's go on if you're ready. Example 3. Well, we've got a function here, and as you can see, it looks like 3 is where the potential problem is going to be. Now with that top expression, since we've got a quadratic in the numerator and x squared, it's tempting to try and factor it. So what x values are going to work here? We need two numbers that are going to multiply to give us positive 3 and combine to give us a negative 4. Well, that's x minus 3 and x minus 1. Well, lucky for us, that does give us a nice cancellation. So that top function is really equivalent to the function x minus 1, except it's not allowed to be equal to 3. It's going to have a hole in the graph at 3 because of the fact that the original expression is just not defined at 3. So otherwise, this is just a function with y-intercept -1 and slope 1. So we know we're crossing here, and then rise over run, and one more time, rise over run. So we know that we essentially go through here, but remember there's a hole in the graph at 3, so that part is an open circle. Otherwise, the function looks like that. So this is the blue part of the function, the top part. Now for the bottom part, the function takes on the value 2. Well, I'm going to put this in a different color so that you can kind of get an idea of what happens. Now the function is telling us that it takes on a y value of 2 when x is 3. Well, when x is 3 and y is 2, lucky for us, what happened is, didn't quite get that different color, there we go. What happens is that hole actually got filled in by that constant 2 there. So what happens here is that the function looks continuous because you could trace the whole thing without actually picking up your pencil. Nevertheless, we're still going to check the 3 conditions of continuity according to the instructions. So the first condition of continuity is that the function is defined at that particular point. Now remember, x is 3 is where we're concerned because that was the only place where anything weird was happening. It caused the denominator of the first function to potentially be 0. But since this was defined in a piecewise manner, f of 3 was defined because they defined it later. So even though it didn't make sense in the first, it makes sense in the second. So this function is defined when x is 3, you're supposed to spit out 2 as your y value. So there's no problem with the first condition. The second condition involves the limit. Now remember, we're concerned about what happens near 3. Well, the limit as x approaches 3 is just going to be 2, right? Because if x equals 3, that doesn't matter. When you're talking about a limit, you're talking about when x is getting close to 3. So we really need to be looking up here. But when x is getting close to 3, you get just a value of 2, right? 3 minus 1 is 2. You could also see it from the graph, right? As x is getting close to 3, no matter which way you're going, the y value there is 2. So the limit is equal to 2, and it exists, so therefore condition 2 is satisfied. Now condition 3 is that the function value has to equal the limit value. Well, that happened here, right? 2 equals 2. So there is no problem, and this is a continuous function at x equals 3. In fact, it's continuous everywhere. But remember, 3 was the spot we were concerned about. Notice how if the original function had just been defined like this, it would not be continuous at 3. But whoever designed this particular function took the extra effort to fill in that hole in the graph and actually made it a continuous function. So again, this particular function, it is actually continuous, so there's no problem here. So if you're ready, we'll move on. Now for example 4 here, we're supposed to be considering the particular function at a equals 0. Well, As we proceed here, this is actually going to be easier than you think. So, condition number 1, remember, is that the function is defined at that particular value. Well, f of 0 here is just what you'd get when you plug in 0 into the function. Well, this is 0 to the power 4 minus 2 times 0 plus 2 over 0 to the 6th plus 2 times 0 to the 4th plus 1. Well, usually with a rational function, that's when you have something in the denominator. You need to worry about where the denominator is 0. Here, we didn't get 0 in the denominator. So what happens is we get 2 over 1 to the power of 10, which is obviously just, I'm not going to multiply that out, but that's obviously just a perfectly fine number, and we've satisfied condition 1. F of 0 is actually defined. What the heck, I'll go ahead and multiply it out. Uh, 2 to the power 10 is, of course, 1024. Okie dokie. And you can just do that in your calculator. That's what I did. Question number 2 is that the limit exists, right? Well, the limit as x approaches 0 of this particular function. Now remember, with limits, you can plug the value in question into the function as long as it doesn't cause it to be undefined, or you're not dealing with infinity in any sort of way. Well, if you plug 0 into the function, I'm not going to redo that calculation because I've already done it, right? You can see that if you plug 0 into that particular above equation, you're just going to get 1024. So the limit as x approaches 0 of the above is actually just going to be 1024. Now part 3 is that the limit from part 1 has to equal, the limit from part 2 has to equal the limit from part 1, and it does, right? Because 1024 equals 1024 no matter what. So actually the third condition is satisfied along with the first and second. So because of that, that is a continuous function. So in this particular problem, f is continuous. So that's done. Now I'm about to erase what's written here, so if you're not finished writing it down, be sure to pause the video to catch up. But if you're ready, I'm going to go ahead and delete that so we can have a little more discussion. Now notice that that particular function could really just be viewed as some function, let's call it f. Doesn't really matter what you call it, but let's suppose I called it f over g, and this is all to the power of a particular number n. Well, notice that the first function is continuous because it's just adding and subtracting functions that we already know are continuous. So is the denominator. The denominator is also continuous. Now remember, you do need to check that the denominator is not 0. But because those x's have even powers, we've got x to the 6th, x to the 4th, and you're adding 1, you're not subtracting, then that denominator is never going to be 0, so we don't even have to worry about that. And lastly, we got a power of 10, and remember we have that theorem that tells us when we divide functions, as long as the denominator is not 0, the result of the division is also going to be continuous, and you can take it to an integer power, still continuous, positive integer power. So you also could use the theorem to reason that f is continuous. Now the instructions told us to do the 3 conditions, so that's what we did, but do realize that the theorem would also apply here. So now we're ready to go on to the next problem. The next problem is asking us a quick question. It wants to know what is the interval of continuity of the following function. So notice that some functions could be continuous just on a particular interval, even if it's not continuous everywhere. Well, the first thing we got to do, that might not be a common function that you're aware of. Let's make sure we can graph this function. We've got f of x equals square root of 9 minus x squared. Well, remember that f of x is the same thing as y. And since I'm intending to graph this, I'm going to write it as y. Now, if you square both sides of the equation, you get y squared equals 9 minus x squared. Of course, at that point, you'd really only be taking the positive part. Think about adding x squared to both sides of the equation. What you really get is x squared plus y squared equals 9. That looks familiar now. That's the graph of a circle. And notice how if you write that 9 in its square form, you'll see that this is a circle of radius 3. So if you graphed this thing, it looks like the circle of radius 3, but there is one problem. The original function was not listed this way. It was actually listed in square root form. Now remember that you cannot take the square root of a negative number. So what that means is you're only getting actually the positive part, which gives you the top part of the circle. So even though x squared plus y squared equals 9 would look like a circle of radius 3, if you're actually graphing square root of 9 minus x squared, you only get the top part. So this particular function looks like this. And it says, what is the interval of continuity? Well, obviously this function cannot be continuous on all real numbers. It's not even defined on all real numbers. But it does look like a nice smooth function. You don't have to pick your pencil up to draw it, between -3 and 3. So the interval of continuity here is actually x is -3 up to 3. But in the interest of discussing continuity, it is important that you're able to take limits, in particular if you have difficult functions. And that includes the trig functions, logarithmic functions, and exponential functions. So what we're going to do is we're going to backtrack a little bit and talk a little bit more about limits here. So if you look at example 1, they're asking us to evaluate the following limit. Cosine squared of x minus 1 over cosine of x minus 1, where x is approaching 0. Well, remember, as long as you don't make the denominator 0, you can actually just plug in for x when finding a limit. That's always true, right? But if you needed to find cosine of 0 down here in the denominator, think about that. Well, that means you're finding the cosine of an angle of 0 on the unit circle. Well, an angle of 0 is actually right here. And remember that the coordinates are cosine comma sine when you're on the unit circle. Well, in this situation, this is the point 1 comma 0, right? X is 1, y is 0. That means that cosine would be 1 there, which would mean you'd be doing 1 minus 1, which would actually give you 0 in the denominator. So because of that, you cannot just try to plug in for x. You're going to need to do some other work or simplification first. So let's go ahead and do that. This is going to be equivalent to the limit as x approaches 0. Now remember when they write cosine squared like that, what they really mean is cosine of x whole thing squared. That putting the 2 near the COS is just a convenience thing. It really means that the whole thing is being squared. So what you really have in the numerator here is a difference of perfect squares. So you can factor it into the sum and difference. Notice how if you FOILed that numerator, you'd get cosine x squared minus cosine x plus cosine x and then minus 1. So the inside and outside terms would cancel out and you'd just be left with cosine squared minus 1. So that is the correct factorization. And you can go ahead and divide this by what was there originally, cosine x minus 1. Well, then cosine x minus 1 cancel. You get limit as x approaches 0 of cosine of x plus 1. And again, you can plug in for 0 now. Cosine of 0 plus 1. And remember, we already discussed cosine of 0 is just 1. So this actually is equivalent to just the number 2. So that's our limit. So we are done with this one. We're going to go ahead and try another example. Again, we're looking at limits with slightly more complicated functions than what we've been doing earlier. Well, look at this one. Now, whenever you're looking at limits, don't miss the obvious. Remember, you always want to try to plug in for the value if you can, because if you can, then it's just an easy calculation. Well, remember, when you're calculating cosine and sine values, you're really looking for values on the unit circle. Now, if the angle is 0, that actually, once again, puts you right here, just like on the last example. Remember, cosine first, sine second. So if the angle is 0, cosine is 1, and sine is 0. So unfortunately, if we tried to plug x equals 0, sine of 0 would be 0, and if you squared it, you'd still get 0. So notice how you cannot just plug in straight for x here, or else you'd get undefined in the denominator. So we're going to have to do some sort of simplification first. Remember that one of the most basic trig identities is that sine squared of x plus cosine squared of x happens to be 1. Well, if you just move cosine squared of x to the other side of the equation, sine squared of x is equivalent to 1 minus that. So, on this original limit, looking at the denominator, sine squared of x can actually be written with its replacement 1 minus cosine squared of x. Well, we still haven't fixed the 0 in the denominator problem though, so we've got to keep going. Remember that cosine of 0 is 1, so we still have the same problem. We haven't fixed anything yet. But if you'll notice that denominator, again, is a difference of perfect squares. So it does factor into 1 minus cosine of x times 1 plus cosine of x. And we're almost at a cancellation here. Notice you can write the numerator as 1 minus cosine of x if you want to. You just need to factor out a negative 1. At that point, you can go ahead and factor cancel, I should say, the 1 minus cosine of x. Here and here. Then we can keep going. So this is equivalent to the limit as x approaches 0 of negative 1 only over 1 plus cosine of x. Now, let's try to plug in for x equals 0 and see if we get lucky. Well, remember that cosine of 0 is just 1. So we got a limit. Nothing is undefined, no problem. And so the limit of this particular complex function actually ends up just being negative 1/2. So if you're ready, what we'll do next is one last example. Limit as x approaches 1 of square root of natural log of x plus arctan of x. Well, let's do some quick review of natural log and arctan, and then we'll go on to calculate this limit. Well, remember that y equals natural log of x looks like this. This is a function that you should have the graph fairly memorized. The logarithmic function. And the arctan function looks like this. The drawing's not awesome, but it does look like this. And the upper and lower limits are negative pi over 2 and positive pi over 2. So just remember that. This is where the arctangent function is defined. Now we are taking the square root of natural log, but notice that natural log is only going to have a problem for square root is only going to have a problem for negative numbers. So notice that after x equals 1, it is negative, which means you're going to have problems with x. It is actually going to only be defined from here on out, which means that it's not going to have a left limit at x equals 1. So because of that, this particular limit actually does not exist. We haven't even considered the arctan part, but the first limit is not going to have a left limit. However, if you did consider just the limit from the right, you might be able to get something. Well, in this situation, you'd be getting square root of natural log of 1 plus arctan of 1. Well, natural log of 1 is just equal to a y value of 0. So that first part, natural log of 1 is just 0. Take the square root of 0, you just get 0. And then from there, you're adding on arctan of 1. Well, arctan of 1. Well, notice that arctan is only defined from negative pi over 2 to pi over 2. So if you're on the unit circle, and you're only looking between from negative pi over 2 to pi over 2, then tangent is equal to sine over cosine. Well, the only way that's going to be equal to 1 is if sine is equal to cosine. And that, again, on this criteria, actually only happens at pi over 2. So because of that, arctan of 1 is actually equal to pi over 2. So this expression becomes 0 plus pi over 2, which of course is just pi over 2. So again, remember that we mentioned the two-sided limit actually didn't exist, but if this problem had been asking for the limit the original problem had been asking for the limit as x approaches 1 from the right of the values at x, you could just plug in 1 and get an answer of pi over 2. So thank you for paying attention, and be sure to ask me if you have any questions. Thank you.